I'm Moshe Babaioff. I'll talk about simplicity in auctions revisited, the primitive complexity, and this is a joint work with Shahar, Dobzinski, and Kupfer. So we're all familiar with combinatorial auctions, in which the challenges are to decide how to allocate items and how to price them. And of course, when considering the design of such auction, we need to take into account communication, computation, incentives, and in many cases, the resulting mechanisms will be very complicated. So there is a lot of research in our community trying to study simple mechanisms or what can be obtained by simple mechanisms, and this is, of course, only a partial list. But what is a simple mechanism? So one criteria that we can try to use is what we call I know it when I see it. For example, when considering selling all the items together as one bundle, this seems to be very simple. Also, selling each item separately, pricing each item, and then the buyer just buys the items that she wants at that price, seems to be very simple. Another mechanism that might be considered simple is bundle size pricing, in which we just set prices per quantities, and then the buyer will just buy the set that he wants, but he will pay the same for every bundles at the same size. Our approach is going to be to consider the first two options as simple and try to capture simplicity by the number of times that we need to run those auctions in order to find the bundles that is best for the buyer, the ones that maximize the utility of the buyer. So let me be more concrete about the setting. We consider one seller and one buyer. We have heterogeneous items, indivisible items. The buyer has, as usual, a private valuation from subset to utilities. They are drawn from a distribution D. The seller commits to a truthful mechanism M, and then the buyer will buy the bundles that will maximize her expected utility, which is the difference between her value and the payment. So it is well known that every single buyer truthful mechanism is just a menu of lotteries. So each entry in this menu is just a lottery and the price for that menu entry, and the buyer will choose the entries that maximize her utility. And of course, there is no reason for the buyer to lie and pick anything else. And also the fact that the menu is has to include the getting zero and paying zero make this mechanism individually rational, because the buyer can always buy the empty set at zero. Now, the size of the menu is the number of entries in that menu, and the menu size was defined by Hart and Nissan as a measure of complexity of a mechanism. So the number of entries in the menu is basically the complexity of the mechanism implemented by that menu. So here's an example of 5-item menu, and we see that there is a list of these 32 different subsets, each with its own price. This seems to be pretty complicated one, but when we look carefully, actually, this is the menu of selling separately. So each one of the 5 items has a price, and as any subset price is just the sum of the prices of the items in the set. So the menu seems very complex, but when we look at it, it's actually not very complicated. It's just selling separately. This is a different menu, and we can see here that all bundles of the same size have the same price. So this is actually a bundle size pricing in which, for example, all subset of price 3 have of size 3 have a price of 12. Okay, so does simplicity imply low menu complexity? So selling separately is widely considered as simple, but if we look at the menu complexity of selling separately, it actually has an exponential menu complexity, which is the maximal menu size over all deterministic menus. The menu size is equivalent to the deterministic communication complexity. So in that sense, selling separately also have the maximal deterministic communication. There are other simplicity measures that were suggested in the literature, but none of them is able to capture the simplicity of selling separately, or it's not fully expressed. So I'm not going to discuss those in details, but as a result of this problem, we are going to suggest a primitive complexity as an alternative. So our intuition is that the menu is simple if we can find a profit maximizing entry in the menu with few simple primitive operations, and selling separately is going to be our primitive operation, and selling separately is widely considered as a simple operation. So we're going to measure the number of primitive operations that we need in order to find a profit maximizing entry in the menu. So what is our primitive? The selling separately primitive is the following. We're going to essentially run a demand query. So we present item prices, and we are getting back a bundle in the demand, ones that maximize the utility. And if there are multiple such bundles, then an adversary will pick which one is returned. And second, the query also returns the value of that demanded set. So in a sense, this is a combination of demand query followed by value query. Okay, so we're going to try to capture the intuition, and we're going to define the primitive complexity of a menu M for class of valuation to be C if there is an algorithm so that for every valuation in the class, find the bundles that maximize the profit of the buyer according to M and uses at most C queries. Note that we are going to insist that the bundles that is returned exactly maximize the profit that is needed in order to ensure that actually we'll have incentive compatibility. This definition can be, of course, extended. The algorithm might be deterministic or randomized. When we count queries, we can count expectation over the Bayesian prior or the worst case over the prior. And also, when we consider which primitive to use, we'll usually think about this combination of demand and value queries, the selling separately operation, but we'll also study the value query setting in which the primitive is just value queries. So few remarks. Selling separately and grand bundle, of course, have primitive complexity of 1 because you just need the one query. For additive valuation, the complexity of every menu is at most M because we can always ask the value of each item separately. And for deterministic menus, the primitive complexity is at most the menu complexity because for every entry in the menu, we can actually run a value query on that set. The main questions that we ask is what is the primitive complexity of bundle size pricing? So here we see again the example of bundle size pricing in which for every size we have a price and we ask what is the primitive complexity of that menu. Okay, so of course the primitive complexity as we discussed is for additive valuations is at most M because we can ask for every item separately. Can this be improved? So our first result is the following. If M is any bundle size pricing menu, and D is a distribution over additive valuation, then for every epsilon that is larger than 0, we can find another menu M prime, also a bundle size pricing menu, that has revenue almost the same as M, but the primitive complexity of that menu is actually only polylogarithmic in M and not linear in M. So we see that we can get exponential improvement over the trivial bound of M. So that's the first result. And let me give you some sense of the proof outline. So here is a menu, a bundle size menu, in which we have list of sizes and the prices for each size. So first approach can be to try to find for every size what is the bundle that has the highest value for that size. And then we look at the difference between the value and the price to see the utility from the best bundle of that size. And if we can do it for every one of these sizes, we'll get, of course, the best bundle, but this will require linearly many problems to be solved, and we want polylogarithmic. So our first step is to decrease the size of the menu without losing too much revenue. So we remove some entries from the menu according to the distribution D, and show that we don't lose too much revenue. But still the menu might be too large. So the second step is actually to show that we don't really need to solve all these problems to solve it for every size, but rather we can actually, at least an expectation, do it for only small subset of this list. So let us formalize that as formal claims. So for additive valuation, there exists a randomized algorithm that finds a k-optimal set, that is a set that maximizes the value given the size, using only polylogarithmic demand and value queries. So this means that we can solve one of the entries. And since there are too many sizes to consider, what the second claim is that for any bundle size pricing menu M, we can find some other menu M prime, which has almost the same revenue, but we can actually find the best entry in that menu M prime using only polylogarithmic many size, consider only polylogarithmic many sizes in expectation over D, and actually a single value query is enough to determine which sizes to look at. So as we saw, the first and the main result is that for additive valuation, there exists a randomized algorithm that find a k-optimal set using polylogarithmic many demand and value queries. Is this tight? So first, see that we consider demand and value queries, and one might ask whether value queries are enough. And we show that with value queries only, even if you use randomization, you will need almost linear number of queries. So you cannot obtain this kind of polylogarithmic positive result. Secondly, we consider moving from randomized algorithm to deterministic algorithm, and then we show that if you consider only deterministic algorithms, then still you need square root m, that is square root m demand and value queries, so there is exponential gap here. And finally, we consider here additive valuations. If you generalize to submodular valuations, which are defined below, then for submodular valuations, you actually need at least exponentially many demand and value queries. This is the most challenging result in the paper, and the proof is completely non-trivial, and I'm not going to actually discuss the proof, and I encourage you to have a look at the paper. In particular, this answers some open problem from 2012. So let me briefly discuss the problem for additive valuation of finding a k-optimal set, that is a set with k items of maximal value. So note that since the items are additive, we just need to find a cutoff such that we'll have k items above that cutoff, and we can do that by essentially binary search using kind of a pivot algorithm. So we pick some element at random. Here we pick the fourth element from the left, and then we sort the items, the ones that higher, and the demand query will return all the items that are higher. It might actually return some items that are equal to that value. If the values are different, then it only returns the items that are higher and maybe that additional item. And then we can decide whether we need to keep searching for higher values or lower values, and using kind of binary search, find it in a polylogarithmic number of queries when the values are, there are no ties. But when there are ties, we are in a different problem. So let's assume that we just want to find the value of the item with the highest value. If there is a huge tie here, most likely we'll pick as a pivot an item from that tie, and then the demand query might return all the items that have equal value. And then if we pick another one, we might still pick an item from the tie and keep getting the same answer with no progress. So we see that this kind of pivot algorithm doesn't really work when there are ties, and we get stuck. So what do we need to do? If we're able to classify items not only to items that are smaller or larger than the threshold, but also particularly the items that have equal value to this threshold, then we'll be able to decide which way do we need to continue searching. So the heart of the result is proving that with polylogarithmic many value and demand queries, we can actually find all the items that have value exactly t. And once we're able to do that, we can run this log m number of times to get a polylogarithmic log cube number of queries to find the k-optimal set. So let me summarize. We suggest the primitive complexity as an alternative to menu complexity, which basically asks how many times we need to run some primitive operation in order to find the bundles that has the highest utility for the buyer. We show that actually we need to combine demand and value queries. Value queries by themselves are too weak to get a good positive results. This primitive complexity is considered selling separately and grand bundle, and selling the grand bundle both have a complexity of 1. For additive buyers, we can find a menu, a bundle size. For any bundle size menu, you can find another bundle size menu that has low primitive complexity and have approximately the same revenue. And then if we want to find k-optimal sets for additive valuations, it's simple. But once we move to submodular valuations, actually we show that we need exponentially many queries. And let me summarize with mentioning few open problems. We have shown that bundle size pricing is simple, but what is the guarantee that it can give? So we know that for IAD agents, either selling separately or selling the grand bundle gives a constant approximation. And but what about correlated symmetric distributions? Is bundle size pricing good for those kind of distribution that gives a constant approximation? Secondly, we want to understand better what's the meaning of low primitive complexity. We know that we can get with just one query, you can get a constant approximation. Let's assume that we want to understand what's the what approximation can we obtain with logarithmically many queries. So with logarithmic primitive complexity, what's the best approximation that we can get, and what's the trade-off between the complexity and the approximation? Thanks very much for listening.